Hey there, everyone, welcome back for day 295, me doing Daily LeetCode challenge after reach 1 year's worth of green contributions here on GitHub. So today's runs for May 7th, 2025. Without further ado, let's get straight into it. Okay, here we go, LeetCode medium, problem 3341, find minimum time to reach last room 1. First things first, I see the word minimum. This is going to be an optimization problem, which is usually either minimizing or maximizing something, which means I'm likely going to be able to resort to either dynamic programming, divide and conquer, or greedy algorithm. Okay. There is a dungeon with n by m rooms arranged as a grid. You're given a 2D array movie time of size n by m, where movie time of ij represents the minimum time in seconds you can start moving to that room. You start at the room 0, 0 at time t equals 0 and can move to an adjacent room. Moving between adjacent rooms takes exactly 1 second. Return the minimum time to reach the room n-1, n-1. Two rooms are adjacent if they share a common wall, either horizontally or vertically. Ooh, okay, so this is going to be a perfect case of UCS or Dijkstra's, whichever one you prefer to say. UCS, if you're not familiar, it's essentially just Dijkstra's, but it's just a little bit lazier, where you don't really write the deltas dictionary to get all the pairs shortest path, even though you can basically get that for free with the same time complexity. UCS is basically just BFS, except use the priority queue, a min heap instead of a queue, right? Or like, you know, same way how DFS and BFS differ by using a stack or queue. UCS is basically the same thing with a priority queue. You just have to be a little careful with the visitations, and that's pretty much it. So here what we can do is x comma y is equal to 0 comma 0. That's going to be our start position. Yeah. Or what we can do is we'll have a fringe, which is equal to a min heap starting with the position 0, 0, 0, as well as the cost, right? So which will be initially a cost of 0, right? Cost, or I can call it time. Time. Oh, and here I'll just have to do a bunch of mins and just a bunch of maxes, right? X comma y, right? And here we'll say go is equal to n comma m is equal to length of move time. I thought it was movies. I'm moving. Okay, yeah. Move time of 0. Right? N by m, just to clarify, it's 2 by 2. This is a what? 2 by 3? Okay. I just want to make sure that I don't get this wrong. Right? While length of fringe is greater than 0, time comma x comma y is equal to heap q dot heap hop from the fringe. Here we'll say here we need a visited set equals sets. Here we'll just say visited dot add x comma y, because this is the optimal time. If x comma y is equal to goal states, then we'll just return time. Yep. Assert x comma y not in visited and add it to visited, and then we'll say for here we need directions. The directions will be 0, 1, 0, negative 1, negative 1 comma 0, and 1 comma 0. Here we'll have an inbounds function is equal to lambda, give me an x and a y, and is it the case that 0 less than or equal to x less than n, and 0 less or equal to y less than m. Now we'll say for dx comma dy in directions, we'll say neighbor of x, neighbor of y is equal to x plus dx, y plus dy. If neighbor x comma neighbor y in visited, continue, otherwise visited, if not inbounds, neighbor x, neighbor y, or it's in visited. I will just have a separate continue statements here. Visited dot add. For now, we won't add as visited. This is what I mean by the careful part. Here we'll say heap q Yeah. If x comma y and visited, continue. Already saw this position with a better time. Okay, heap q dot heap push. So the new cost, new time will be equal to the max, right? So it'll either be or maybe we can just say wait. Minimum time required is 6 seconds. Yeah, let's see an example. So here, yeah, I need to see an example just to make sure. For 4, output is 6. At time t equals 4, you move from 0, 0 to 1, 0. Oh, I see. So at exactly this time, I can be there. Right? Required time to move. Here we'll say if time plus 1 is greater than or equal to move time of neighbor x, neighbor y, then we'll add it in here. Right? Heap q dot heap push. Time plus 1, neighbor x, neighbor y. And here we'll just say raised exception, no solution found, which should not happen. Okay, let's see if something like this works. Heap q, yep, if I misspell heap q, that'll do it. Heap q. No solution found, really? Am I getting this wrong? Should it be mn? No. Reverse. Okay. Okay. Here we'll say visited.add neighbor x, neighbor y. Yeah, but that's the problem with UCS, right? You can't do things this way. Actually, wait. Why don't I just do this? Heap q dot heap push, the max new time to reach nay is equal to max between moving there instantly and the actual thing. Move time, neighbor x, neighbor y. Right? And then here, this neighbor x, neighbor y. Okay? Yeah. So now, just like this. We'll do this. First of all, how the hell? Yeah, so this should all be like this, and this will be into the fringe. That's my bad. Okay, so now I'm getting incorrect solutions. I see, I'm having +1 issues here. Yeah, it's about distance, right? Yeah, there's an element of distance. I can't just get away with something like this. Okay, let's see an example. So what's going on here? It's to 1, 1. This is to get it here to 2. So what does it work for case 2? Everything's 0. This shouldn't be +1, right? Or should it? Okay, I suppose so. Let's submit. And there we go. Complete streak 395 days. Consistency is key. See ya tomorrow. Okay, sweet. Yeah, so it's just going to be the max between the current time and, well, the minimum time to get there, all +1, right? That's the idea. Makes sense to me. And it was just working for this one because everything is 0, so it's just going to win every time with a +1. Makes sense to me. Makes sense to me. Okay, yeah. This is a little slow. So the question is, can I get away with this? Neighbor Y. Or will it not work for UCS? Also, I can disable my flux just so that my screen is a little bit brighter here. Yeah, this is a little problematic. Maybe that doesn't really help. I could put in 0, 0 in here. Helps a little bit. Helps a little bit. Does help a little bit. Maybe that's a better way, right? Versus this and this and nothing here, right? I guess it's the same. Sure. This just makes me feel safer because it's like it has to be correct. Whereas the other way, it's like I always gotta think a little bit. Yeah, so if this or this, then continue. Otherwise, or better yet, and this not invisited. This you might as well put here. If reached goal state, no. With optimal time, so UCS, da-da-da. Ba-ding, 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 ba-ding. Yeah, we wouldn't want to do that. Yeah, there we go. And now we're at 26 measly %. Okay, well, alrighty, Roo then. I see how it is. So it's just faster if I do visited at neighbor X, neighbor Y here. Leave this out. Put in 0. It's just that I swear sometimes UCS does more for that. But yeah. I guess it's just in this one. It's like you might as well like expand everything. Blah blah blah. Yeah. So yeah, here you'll get an 80.11% solution. So I could leave it as is, just yeah. Makes me more uncomfortable, you know, but oh well, okay. So I will leave it as even though this is correct for this problem with the 743 test cases, I'm a speed junkie. I like speed. So you know what? We're putting this. I like speed. Please don't judge me. Please don't judge Yeah, okay. There we go. Okay, so nevertheless, as always on my videos, I do a quick recap of advisor solve problems. So this one, this is literally dexterous. That's this problem, right? So you're given an m by m room, arranged as a grid. You start in the top left corner, 0, 0. You want to get to the bottom right corner, m minus 1, m minus 1, in the shortest amount of time. Classic little problem where your neighbors are essentially, it's like for a cell, you can either go up, down, left, or right. And the only caveat here is that, well, moving between rooms costs 1, but each room has a minimum time at which you can enter it, right? So for example, this room, you can enter it at starting from time t equals 0. This one starting from time t equal 4, time t equal 4, time t equal 4. So literally, my solution is just basic UCS, which is just Dijkstra's, but you just don't keep track of the all shortest path dictionary and so on, just because I'm lazy. UCS stands for uniform cost search. So if you know BFS or DFS, you know that those either use a stack or queue. UCS is basically the same thing with a min heap or priority queue. A star search is UCS. So UCS is A star search with a 0 heuristic, right? So whatever way you need to understand it, UCS is just basically Dijkstra's, or just BFS or DFS with a min heap instead, or just A star search with a 0 heuristic. However way you understand it, this is what I've implemented. I just do a basic UCS to essentially get the minimum cost from the top left corner, which is 0, 0, all the way up to the bottom right corner. The only thing I do newly is accounting for the minimum times at which you can reach a room, right? So here I just have, okay, n comma m, or my dimensions of move time. My goal state is m minus 1, m minus 1. The directions at which I can go from any cell, well, it'll be like, you know, these are my delta x, delta y's, right? So for example, 0, 1 means move 0 rows, move 1 column to the right? 0, negative 1 is move 0 rows, negative 1, so 1 column to the left, right? This is 1 row up, this is 1 row down, etc. So all 4 possible directions. Inbounds just checks like, okay, given an x, y, is it the case that 0 less than or equal to x less than n and 0 less than or equal to y less than m, i.e. is it inbounds of my grid, right? Then all I do is like, okay, visited set, I start at 0, 0, so I'm just gonna mark that as my visited. I might as well put it below my fringe. So here I have a fringe, which is my min heap, right, my priority queue, which is always elements that are tuples of 3, where the first one is the cost, or the time in this case. The second one is the x-coordinate, the third one is the y-coordinate, right? Initially, we're at 0, 0, and 0, 0, 0 is the only thing on our fringe. We're at time t equals 0, coordinate 0, 0, right? And we've visited only the coordinate 0, 0 at the very beginning. Then we'll say, okay, while we still have stuff in the fringe, right? We can also say while fringe, we're gonna pop the elements from a fringe with minimum time, right? Then we're going to say, okay, first of all, if this is the goal state, we're done, because with UCS, the very first time you see a goal state might not be the optimal solution, but the very first time you pop a goal state will be the optimal solution. So here we just pop something. If xy is equal to goal state, we know this will be the optimal time by UCS, so we return that time because that is the optimal time, i.e. the minimum time to reach the last room. Otherwise, we'll be like, okay, we haven't reached a goal state, let's look through all of our possible neighbors. So for dx, dy, and directions, let's get the neighbor coordinates. Neighbor x, neighbor y is equal to x plus dx, y plus dy. And then we'll say, okay, if that neighbor is in bounds of the grid and it's not been visited before, then okay, there's some awesome stuff we can do over here. So first of all, we'll add this neighbor, right? And here we'll say, okay, what is the time to reach this neighbor? Well, it's not just going to be our current time plus 1, right? If our current time is smaller than the minimum time at which we can reach this neighbor, then we must wait that much time before we actually reach this neighbor, right? Which is why I'm going to take the max between time and move time, right? If my current time is greater or equal to the minimum move time of the neighbor, great. I don't have to wait anymore, right? But if, like, you know, the minimum move time of the neighbor is 10 and my current time is 3, I need to wait 7 seconds before I can actually go to this neighbor's room, right? And then the maximum between these two, I'm going to add plus 1 to it for the cost of actually moving to the neighbor. And that'll be the new time, right? So here then I'll just add it to my heap with that new time to reach the neighbor, the new x coordinate, the new y coordinate, and then add that to my visited set. and I'll just keep doing this until I reach the goal state, and there we go, bada bing, bada boom. Now the only thing is that, like, you know, for the cases of this problem, this might work, but usually with UCS, what I do is I don't do the visiting here. What I do is, like, you know, since I know that whenever I pop something from the heap, it's always the optimal solution, usually I do the visiting there. So what I do is usually here I'll say, like, you know, if x comma y in visited, then, you know, here we'll say continue, already visited this position with better time before, with smaller time before. Otherwise, we'll do visited dot add x comma y, right? And here we'll obviously not have this. Beauty. Okay, so time comma if goal state, yeah. So usually I do this. Now you'll realize that I had about 80% solution here. I'm going to go way down to the 20-30 seconds and so on. But I prefer this way of writing it just because I know crystal clear no matter what that this is completely correct and not just, like, you know, lack of test cases, even though that's probably not the case. It's 743 out of 743. The point is with UCS, you know that you reach a position with optimal time whenever you pop something, not whenever you see something through your neighbors, right? Which is why that as soon as I don't check if I see the goal state in here, I check if I see the goal state in here, right? So whenever I pop something, I can be sure that that's the minimum time. Same thing with Dijkstra's, right? Whenever it's, like, you know, the new next element you look at, you know that you reach that one with optimal time, so you update your dictionary of the shortest path from the source node to that current node because you know that's set, and then continue onwards greedily, right? So I prefer keeping an empty visited set and being like, okay, if I ever visit something that's already my visited set, then that means it's, like, you know, terrible information because I've already seen this node before with even less time. So this cannot help me reach a better time, right? I'm at even more time. It can either be the same time or more, right? Which is bad because I want to minimize. So in that case, I'll just continue. Otherwise, it's like, okay, we haven't visited it, so let's add it to our visit set, and then just keep going through this thing, right? It's just that you might end up, like, you know, visiting things more often than once, so it'll definitely make the solution a little bit slower. But in terms of, like, you know, paranoia, if you're a paranoid guy like me, I do like writing it this way a little better. But obviously, the other way will be a little faster, and it does pass the test cases for this problem. It's just that I tend to be a little bit paranoid sometimes. But yeah, otherwise that's literally the entire solution. It's just Dijkstra's, UCS, whatever you want to use. The only caveat is that, you know, instead of saying the cost is exactly just like, you know, current time plus 1, it's like you just take the max between the current time and the minimum time required to enter that room, take the max of those two, and then add 1, right? Just so that you respect the fact that these rooms have a minimum entry time. And there you go. Otherwise, it's just regular Dijkstra's with just that one little twist. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.